Hello everyone, my name is Darlene Attila Leng and welcome to my presentation video on how to measure using a multimeter. So, this is a mini project for the subject KNR 1042 Instrumentation and Measurements. The objective of this project is to demonstrate the capability to construct electrical and electronics related experiments based on specific requirement by the tutor using the provided components and tools, to understand the circuit diagram provided and construct the circuit physically, then to calculate the theoretical value of total voltage, partial voltages, total current and partial current of the circuit, and next to demonstrate the steps on how to use the multimeter and to measure the total voltage, partial voltages, total current and partial current measurements of the circuit using the multimeter. Right, so let's go straight into the presentation. Okay, so the scope of the presentation would be the introduction, then the circuit, then the experiment procedures, calculation of theoretical values, video demonstration of how the measurements were taken using a multimeter, calculation of theoretical values based on actual resistor values, results, discussion, then conclusion and recommendations. Okay, so let's go straight to our introduction. What is a multimeter? Okay. So what is a digital multimeter? A digital multimeter is a test instrument that has been widely used in electrical industries to measure quantities such as voltage, current, and resistance. It is a standard diagnostic tool for technicians in the electrical and electronic industries. Okay, the face of a digital multimeter typically includes four components, which is the display to view the measurement readouts, okay, the buttons to select various functions. So that's our button there, and I think the options vary according to model, okay, and then a dial or a rotary switch to select primary measurement values such as volts, amps, and ohms. So in this image, our ammeter section is there, our voltmeter section is there, and our ohmmeter section is there, and then is using this rotary sort of like dial as well for us to select the range for the voltmeter, ohmmeter, and ammeter for each section. And of course, it needs to have an input jacks, which is that. So where the test leads are inserted, so the red one is always our positive and the black one is the negative. So when you have your multimeter, make sure that you insert your leads correctly with the correct polarity, okay? So, right. So let's go straight into the experiment. So this is the circuit that the lecturer has requested for us to construct. As you can see, it is a simple circuit with three 1K ohm resistors, two in parallel, one in series. And to draw this circuit, I've used a free user-friendly program online for making electronic circuit diagrams called Circuit Diagram. So the link is shown on the screen if anyone is interested. So this is the circuit again, but this time I've labeled our circuit with the resistors R1, R2, R3 and test points A, B, C, D, E, F, G, H, I. So these are the points that we are going to, number one, theoretically calculate the values, and number two, measure using the multimeter, so we can compare the theoretical measurements and the theoretical calculations and the measurements. Okay. So this is the experiment procedure. Okay. So the circuit is constructed as shown in the figure above, which consists of three 1K ohm resistors and one 1.5 volt battery. The theoretical data were calculated and recorded as shown in table 5.1, table 5.2 using the formula V equals to IR. R2 and R3 are in parallel, so we can calculate R23 using the formula R2 times R3 divided by R2 plus R3, and R1 is then in series to R23, so the total will be R1 in series to R23, so R1 plus R23. Okay. And then the third one, the partial and total current is then measured and recorded at test points A, B, D, E, F, G, and H, I. Okay. So the partial voltages at test points BC, EI, and GI is also measured and recorded using the multimeter. And then after that, we would compare the measured and theoretical data. So, before we start our experiment, it is important to measure the theoretical values first so we can select the correct range on our multimeter when doing our measurements. Okay, so the calculation of theoretical values is calculated like this, okay? So the total resistance, as we can see, R2 and R3, they're in parallel of each other. So to calculate that, R2 times R3 divided by R2 plus R3. So we get R23. Then we can see that R2 and R3 is then in series to R1. So R23 plus R1, so we get the total current, total resistance of 1.5 kilo ohm. Okay, so the total current can easily be measured with V equals to IR. So we get the total current of 1 milliampere. Okay, the current at test points AB and HI, okay, this is due to AB and HI, they are in series. So the current at test points AB and HI, so which is I1 is equals to I total, then the total current, which is 1 milliampere. And then the current at test points DE and FG. So based on from the current divider rule formula, we can calculate this using I2 equals to R3 divided by R2 plus R3 times I1. So we get 0.5 milliampere. And similar to I3. So I3 is R2 divided by R2 plus R3 times I1. So we get, so for the current is at I3 is 0.5 milliampere. Okay, and the partial voltages at test points BC and EI and GI for resistors R1, R2, and R3, we can calculate with the formula V equals to IR. So for resistor R1, so we know that I1 is 1 milliampere and our R is 1 kilo ohm. So we get 1 volt. Okay, and similar to V2, we know that our R2 is 1 kilo ohm as well, but our I2 is 0.5 milliohm ohm. So we get V voltage at resistor 2 is 0.5 volt, and similarly voltage at resistor 3 is 0.5 volt. So the total voltage at test points BI is 1.5 volt. So that's the battery. Okay, so right, so with that, let us watch the video of how the circuit is constructed. So how we take the measurements of the measurements of the actual resistance of the 1k ohm, and how do we measure the current and voltage for the test points using a multimeter. So enjoy the video. Right, so good morning or evening everyone. So before we start our experiment, first of all, it's important to check the actual resistance of our 1k ohm resistors. So to do that, we have our multimeter here. So first of all, make sure that your multimeter terminal is connected properly, which is the red one is a positive one, and then the black one with the negative one. So first of all, that's a 1k ohm resistor. So what you do is you make sure that the setting of the multimeter is correct lah. So 1k ohm, so you make sure it's at 20k. Okay, so now let's measure R1. Okay, R1, you just connect one of the leg to the probe and the other one to the other end. There you go. So you wait until it stabilize. Okay, so that's 0.97 kilo ohms, so it's equivalent to 970 ohms. Okay, the second one, R2 is 0.97 kilo ohms, correct, and R3 is 0.98 kilo ohms. Okay, so now that we've taken the values of our resistors, so let's start assembling our circuit. Alright, so now let's set up our circuit on the breadboard. Okay, so first of all, you know that this is the given circuit by the lecturer. So that is 1.5 volts battery, which is that, and then you have R1, and R2 and R3 are in parallel of each other, okay? And R1 is in series of R2, 3. So let's set it up. So the first thing you need to do is, first of all, I would like to set up my R3. So let's do this. Okay. Yeah. It's a bit tricky. I don't know why. Okay. Get your R3 in. There you go. Okay. Then you get your R2. So R2, because in our breadboard, like it's connected that way. See, it's connected like that. Okay. It's all connected like this and like this and like this lah. So we make sure that since our R2 is parallel to R3, we can skip one of this, but then we can stick it there so that's clearer, not so congested. Oops. Okay. So here we have our R3. Make sure the R2 is in R2. And then our R1. So our R1 is in series of R2, 3. So we make sure that we have the feet there. It's correct. And then it goes there. Okay. So here is positive. So we make sure sorry. It's connected there. And the negative is connected to the negative feet. There you go. So there you go. So it's I hope it's clear. So you can see it's our battery, which is there. Then you see R1, which is here. Then you see R2, which is there, and R3, which is here. So these two are parallel and that's series to these two. Okay, so that's the circuit setup. So after this, we are going to learn on how to read each partial voltages, and yeah, that's it. Right. Okay, so now let's measure the total current, milliampere, and the partial current, milliampere, for our circuit. Okay, so first of all, we want to measure the total current at AB and at HI. Okay, so based on our circuit, that's our AB here. So between the positive terminal of the battery and the resistor R1, and our HI is here, so that's our H and that's our I. Okay, between the negative terminal of the battery and the leg of the R2 resistor I. Okay, so right, so let's measure our total current at AB and HI. So based on our theoretical measurement, we know that the values of the rough values of the total current AB and HI is around 1 milliampere. So we make sure that we set up the multimeter properly. So make sure that it's at ampere. Let's put it at 20 milliampere. Okay. All right. So let's measure AB first. So yeah. So pull the leg out. Okay. So make sure that if this is red, so that's positive. So make sure that the probe is correct. So red to red. Make sure I don't block the multimeter as well. Oops, sorry. Ayo, can you see? Can you see the values? Okay. Wait, okay. And make sure that the black one is touching the leg. So we get 1 milliampere. Okay, so the value of total current between A and B is 1 milliampere. Okay, let's pull this one out. Put this one back in. Okay, sabar. All right. Oops. A bit tricky. Okay. Right. So the next value would be the value of HI. Okay. So what you do is you pull out the negative leg, and then you make sure black one, negative terminal touching there, and then the positive one touching there. So we get 1 milliampere. So the value of the measured value of total current for HI is also 1 milliampere. Okay. So now let's put it back in. Okay. Right. So now let's measure the partial current at DE and FG. Okay, to do that, let me just zoom in to my breadboard. Is it zoom enough? That's enough, I guess. Okay, so DE, if you can see here, okay, so move this away. So that is our D, okay, this is our D, and that is our E for our R2, okay, so R2, so that's our D, and that's our E. And for our R3, which is this guy, so that's our F, that is our G, okay, so F, so a G. So to measure that, let me bring my thingy back. Oops. Okay, to measure that, what we need to do is, first of all, to measure DE, we need to pull up one leg, okay, and then we need to take a wire, okay, so we need to stick the wire like where the leg is to be, okay, so where the wire comes in, so that is positive, so positive, so this is positive, okay, so make sure positive there, make sure, okay, so make sure our positive is here and our negative is at this feet. That's already loose, so we get 0.5 milliampere, okay, at DE. Right, so let's pull this back out, put this back in. Okay, so now the value of partial current at FG, same thing, pull out the F and poke the wire into where the leg is to be. Make sure that that is your positive, again, positive. And then this one, negative. Yeah, okay. So we get 0.5 milliampere as well for FG. Okay, so now we've measured the total current and partial current at AB, HI, DE, and FG. Okay, so let me put this back. So after this, we are going to measure our partial voltage and total voltage. Alright, so now let's measure our total voltage and partial voltage. Okay, so for our partial voltage, we're going to measure it at BC. So for resistor 1, to measure the partial voltage for resistor 1. And then we're going to measure the partial voltage at EI. So that's how we measure the partial voltage at resistor 2. And at GI, and that's for the partial voltage for resistor 3, and the total voltage which is at HI. Okay, so this is how we do it. This is how we measure the partial voltage. So let me show you how to measure the partial voltage for resistor 1 first, okay, which is the BC. So that is simple. So what you need to do is, we know that from our theoretical calculations that the highest voltage for this would be 1.5 volts. So we just make sure that we set it up properly. So 20 volts. Okay, that's enough. Okay, so let's measure for R1 first. So at BC, so you make sure that's positive. So positive. So hopefully you can see the multimeter. Okay, this. Oops. Okay. Not stable. Hold on. Okay, so it's 0.97. Oops. Okay, so 0.97 volts for that. And then for the measurement for partial voltage for resistor number 2, so that's resistor number 2, so positive, negative, negative. Okay, let's try. So what do we get? So we get 0.48. Okay, so for partial voltage for resistor number 3 at FG, so you do that and that. So you get 0.48, okay? So to measure the total voltage, now you cabut this kaki. Oh no, you just go that. So for our battery is positive, positive, negative, negative kaki for the battery. So you get 1.47 voltage. Okay, thank you very much for watching. Alright, so in the video you have seen that we've actually calculated the actual values of the resistors and a battery using a multimeter. So it is important that we use the true measured value of the resistor obtained when calculating the theoretical values, when we want to compare between the measured values and the theoretical values. Okay, this is so that we can make sure that we can compare apples to apples, when comparing the results. Okay, so how do we calculate the theoretical values based on the actual resistor values? So the steps is the same as how you calculate the theoretical values. It's just that you substitute the you use the actual values, which is 970 ohm for R1, R2 970 ohm, and R3 980 ohm, and the voltage that we measured in the video, as you can see, was 1.47 volt. So with that we get a total resistance of 1457.5 ohm, and the total current is still 1 milliamp, and the current at test points A, B, and HI is still 1 milliamp. I2 and I3 is slightly different at 0.51 milliamp, and the partial voltage at test points for R1 is 0.97 volt, R2 is 0.49 volt, and R3 is 0.49 volt. Okay, so let us compare the results. Okay, so this is the result that we have obtained. Okay, so from the result, okay, so this is the test point. So this is the measured and theoretical value of the current at test points D, E, F, G, A, B, and HI. And this is the table with the measured and theoretical value of the voltage at resistor 1, so B, C, EI at resistor 2, and GI at resistor 3. Okay, so from the results, you can see that first of all, the theoretical values of the partial current at DE and FG is 0.51 milliampere, and the total current is 1 milliampere. Whereas for the measured is 0.5 milliampere, and total current is the same at 1 milliampere. Okay, as for the partial voltages at resistor 1, 2, 3, we can see that for the for the resistor R1, the measured theoretical value is the same at a 0.97 voltage, and then at R2 is slightly different. So for the measured we get 0.48, and for the theoretical we get 0.49, and for R3 it's slightly different as well, with the measured at 0.48 and the theoretical at 0.49, and the total voltages is, we've used that to calculate our theoretical value, so that should be the same at 1.47 volts. Okay, so right, so comparing the results. Okay, so with that we sort of like find out the discrepancy between the theoretical value and the measured value. Okay, so we should use theoretical minus measured value divide by theoretical times 100%. So we can see that the difference between the theoretical measured value for the partial currents at DE and FG is 2%, whereas the total current is the same, is 0%. And the partial voltage for our resistors, so for R1 is the same, so 0% discrepancy, but for R2 and R3 is 2%. And the total voltage, of course, is 0% because we have used that to measure our theoretical value. Okay, so that's our results. Okay, right, so let's go into our discussion. Okay, so first of all, it is important to firstly calculate the theoretical value. This is so that the estimated current range of the ammeter could be obtained, so that the correct range could be selected to avoid damaging the multimeter. Or sometimes if you select a range that's too high, you are not able to read it. So you may have to make sure that you select the range properly, and then and then the other reason why you need to measure the theoretical value is that you do not want to destroy your equipment. So you should make sure that the equipment that you use, the range is is okay for what you want to measure. So it's important to, first of all, in any situation, it's very good practice to measure the theoretical value. Okay, then the true measure value of the resistor arm obtained must be used when calculating the theoretical values. Okay, here as you can see at the start of the experiment, so first of all we measure the theoretical value first using what the lecturer has requested, so 1k ohm. So that would then help us to select the correct equipment with the correct range. Okay, then when we want to do the experiment, we measure again for the resistor what is the actual resistor value, you know, in ohms. Okay, and then with this we use this value to then calculate again our theoretical values, so that we can compare that theoretical values, you know, of the actual measured resistor values and compare that with what we actually measure using the multimeter. Okay, so that we can make sure that we're comparing the same thing, not apples and apples. Okay, so then after that we have to also check for equipment error. So the actual measured value can be adjusted based on the error of the multimeter, okay, or our equipment. In this situation, in our video, as you can see, the multimeter shows a value of 0 milliampere and 0 volt when it is not connected to the circuit. Hence, there is no need to adjust the measured value as there is no error. Okay, but if there is an error, you have to make sure that you adjust the values by, you know, for example, if before you do anything, you can see that your ammeter range is a 0.01 milliampere. So you have to make sure you minus a 0.01 when you get your, you know, reading. Okay, and so forth. Okay, so table 5.3 and 5.4 just now shows that there is a slight discrepancy between the measured and theoretical value, which is probably due to the systematic error of the multimeter. And the other factor that might cause the discrepancy between the measured and theoretical value is the rounding error. Okay. Right, so in conclusion, okay, the calculation for the total voltage, partial voltages, total current and partial current can be calculated using the formula V equals to IR and the current divider rule. The reasons why there is a discrepancy between the measured and theoretical value taken and shown in table 5.1 and 5.2, even it's very slightly, is due to systematic error and the rounding error. Okay, so I believe that I was able to demonstrate my knowledge and skill to construct the electrical and electronics, to construct the circuit, you know, based on the specific requirement by the tutor using the provided components and tools. I was also able to demonstrate how to use the multimeter, I hope clearly. I hope every one of you learned how to use it based on my video. I hope it was useful for everyone. I hope everyone learned something from it. So I believe the objective has been achieved. Okay. Right, so the recommendations, okay, so this is my recommendations. Okay, first of all, as I've said in my discussion, it is important to firstly calculate the theoretical value of the measured data so we can select the correct range for the equipment to avoid damaging the equipment. Okay, it's also important that we check for any errors in our components and equipment in order to get good quality data which is precise and accurate. And the equipment, so in our case it's a multimeter, but if you have any other equipment, okay, must be periodically calibrated as per manufacturer specification so that the data measured is as accurate as possible. Okay, systematic error can be eliminated not totally but to a sufficient degree through calibration. So calibration is simply a procedure where the result of the measurement recorded by an instrument is compared with the measurement result of a standard. Okay, so it's also important to understand the effects of rounding error, as errors can be magnified, you know, or accumulated when a sequence of calculations is applied on an initial input with round-off error due to inexact representation. Okay, when different kinds of number of representations are used together in complex engineering systems such as rockets and missiles, they can fail catastrophically and even cost lives. So as digital computers right now, you know, are integrated into larger and larger socio-technical and physical systems, we must be even more careful when it comes to rounding error. Okay, so in our situation, it's just measuring the 1k ohm, you know, but imagine in a situation whereby the computer is, you know, generating, you know, and we're using that data to, like, you know, generate more data. So, you know, so we have to be aware and take into account any rounding error when doing our calculations and our design. Okay, so that is it. So this is the references for my presentation and my report, which I'll be submitting to the lecturer. And thank you very much for watching, and I hope you have enjoyed my video and you're able to learn something from it, because it took quite a long time for me to do this video because I'm not used to doing videos. Okay, thank you very much. See you again.